Alright, hey guys, what's going on? So today we're going to be covering relativistic momentum in light coordinates. So in the last video on string theory, we talked about light coordinates and we sort of briefly started to talk about relativistic energy and momentum. Now we're going to bring those two things together and we're going to understand a little bit more about how these two things indeed do fit together, and then we're going to go from there, we're going to go into quantum mechanics. Okay, so make sure to hit that like and subscribe button. Make sure to go into my Patreon page if you want to support there. You can become a member here on YouTube as well if you want to get all of it. This is, again, going to be free. The first few videos in string theory are going to be free. So let's go ahead and get started. We're talking about relativistic momentum in light coordinates, or light cone coordinates today. And this is probably going to be a short video. We'll see how fast I talk here, but we want to take everything we know now about relativistic energy momentum and our light coordinates, and we're going to apply the two. So we're going to say that for a relativistic particle, its light cone coordinates, or its light cone momentum coordinates, are going to be depicted in this way. So just like we did for our light cone coordinates, where we had P plus and P minus, or where we had X plus and X minus, we have now, we're going to define these two things, okay? And we can notice here that this is the negative of P minus, P underscore minus. We'll see how this works later. All right, so with these two in mind, we can, in the last video, we identified the light cone time to be X plus, and so we're going to aim to figure out what exactly the corresponding light cone momentum is going to be. Recall that the line element between any two vectors in our four-dimensional space is this thing right here. And in flat Minkowski coordinates, we found out that the momentum is equal to this. It's the temporal component of the 4 vector which defined our 4 momentum. Okay, and in our light cone coordinates, we don't know what this is yet. This is what we're going to try to figure out. All right, so to understand the momentum component of our 4 vector in our light cone coordinates, consider a wave function for some particle that obeys the Schrödinger equation. So here's our Schrödinger equation, and this is going to be our temporal component, E over C. So the time derivative of our probability distribution, which is the solution to our Schrödinger equation, has an eigenvalue. So this momentum operator has an eigenvalue that's E over C, and in special relativity cases, C is usually always equal to 1 times the function itself. So again, this is saying whenever we're dealing with eigenvalue problems, we are looking for we have an operator on one side of the equation, and we have just a number on the other side of the equation. Okay. And so really what this means is that with this psi here cannot be just any arbitrary psi. It has to fit this equation such that when you take the temporal derivative of it, you only get a scale multiple back. Okay. So this is actually a very constraining equation, because it gives us the form of psi has to obey this rule. All right, so in our light cone coordinates, so we called this thing the time component. So we're going to switch x0 with x plus, and we're going to say ELC, which stands for light cone. Okay, and the energy of the light cone divided by C, the same form as we did up here. Everything's now in the light cone coordinates. Okay. The solution to the Schrödinger equation is but the solution to the Schrödinger equation is this guy here, where we have P0, X0. P0 corresponds to the frequency along the X0 direction, and then the spatial portions there. All right. So if we recall from the last video, we had a lot of these new identifications for the light cone coordinates, where we had A plus equals A minus, the negative of A minus equals the negative of A plus. We also established this rule here, which was this guy right here. Okay, this helped us define our this thing again. This, oh, I'm going to decrease the size of my pen like that. ds squared. So this guy helped us in establishing that, right? Which was this guy right here. This means that according to equations 3, 7, and 8, right? So this is why I label equations, to go through this relatively quickly. 3, 7, and 8, we can rewrite this. We can rewrite our solution in this way, where we're contracting pluses with each other, minuses with each other, and then our two other remaining spatial dimensions. And so in special relativity, our Schrödinger equation then becomes this right here, right? So the eigenvalue now is the momentum, is the plus momentum, the negative of that. Okay. All right. According to equation 5, okay, so I'll just go back to equation 5 really quick. This guy right here. This means that the light cone energy becomes the eigenvalue associated with P plus, and we can say this then. So we have the eigenvalue associated with this is, in terms of energy, is the energy of our light cone divided by C. But again, according to these relationships here, we can easily find out that, just through a little bit of algebra, that the P negative is the same thing. Okay. All right. So now recall and also from these, these guys as well. These guys help also. All right. So now recall the relativistic four-momentum equation. So that's this guy right here. Normally we see this as, right, this is, actually no, I don't have to recap on that. So this is something that should be easily recalled. This is the relativistic four-momentum. This is the temporal component of that, where again P0 is E over C squared, or if P T squared. It's like that. All right. And so from that, our particle is traveling in just the x direction, and we can say, so if our particle is just traveling in the x direction, this thing is going to reduce down just to the x direction, which is P1. And so we get this, and then doing some math, we can get this guy here, right? We're just extracting P1 out, so we have to divide this by P1. Then the square root of this is just P1, this, and then through the binomial approximation method, we get this. Again, the binomial approximation, really, if you're not aware of that, you can look that up. It's not too difficult to see that this bit right here is all of this right in here. All right. So this means that we can rewrite the light cone momentum as, so this is what our light cone momentum was. And so we have this, which is P0, okay? So we put in for P0, this right here. We can see P1 cancels out with P1, all right? And then we get this guy right here. So this is 1 over root 2 m squared c squared over 2 P1. And so given the first equation from 7, right, so first equation from 7, which is this guy right here, and the equation from 2, this guy right here, so P minus equals the negative of P plus, and then A plus equals the negative of A minus. Well, the two negatives are going to cancel, we get this guy. So rewriting equation 12 then, we get this. All right. That our light cone energy is related to our momentum in this way. So if we do a little bit more math, we could take the reciprocal of both sides and then isolate P1 and we get this. So this is interesting, and this is what we're looking for, because we can see that as the light cone energy decreases, the momentum increases of our particle, okay? We saw in the beginning of this analysis that we chose the light cone time to be x plus, okay? And in the last video, we were also able to see that as the velocity of the particle increased, the light cone velocity decreased. So let's look at this in terms of a picture here. So as the light cone energy decreases, our momentum, right, according to this equation, increased, right, because they're reciprocally related to each other through this quotient right, this quotient right here. DSimilarly, when we looked at our light cone velocity and our velocity in Minkowski coordinates, we had our dx minus over dx plus equals 1 minus beta over 1 plus beta. So this is from that. We saw an inverse relationship again as we decrease velocity in the betas, then our light cone velocity decreased. So this is what we're looking for, right? Because we want these things to match, right? Because we don't want this to increase as this decreases, because we're looking for something that becomes more relativistic in the light cone coordinates. And so as these things increase, as momentum velocity increases, then we are looking for particles that get closer and closer to the speed of light, or that's what we're looking at. We're looking at particles that get closer and closer to the speed of light. So as that's them corresponding to them becoming more relativistic. As they become more relativistic, something's got to happen in the light cone coordinates, and we want those two things to match because these two guys match, right? So this is how we get them to match, right? So we get these things to match, and again, these are the coordinates, okay? And yeah, so again, I paused there just to make sure I was saying right things here. But again, the idea also, if the velocity increases, or here the velocity is going to decrease here in our light cone coordinates. But if the light cone coordinates decrease, then this is actually going to increase, because remember, as you move, if we look at just simple relativistic, so here's our light cone line, here's x and here's t. As particles become faster, when we're looking at E equals mc squared again, or our relativistic, actually let's do our relativistic energy, our relativistic energy again is m squared c squared equals E squared over c squared minus p dot p. Like that. That's our relativistic energy. If our momentum is zero, then we just get E equals mc squared, right? And so the momentum decreases. The energy then is going to all the energy is put into the temporal component, right? So it's not necessarily true that if this is actually inversely true. If this decreases, then this thing has to increase, right? So these two things are inversely related to each other, but these across here, they're also inversely related to each other. So that's just that's the point I want to get across, because in special relativity, we have these relationships where if you're moving closer to the speed of light, your rest energy becomes you have less and less rest energy, which is at E equals mc squared. All right. So that's really all I want to go through in this, because I kind of want these to stay on topic. In the next topic on this, we're going to start going through a little bit of a review on quantum mechanics. Okay, and we're going to slowly build up to string theory. And so this might be a review for you, or this might not be. The idea here again is that we want to review special relativity as most and as efficiently as we can before we dive into the very complex topic of strings. So with that being said, make sure to hit that like and subscribe button. You can also go into my Patreon page if you want to support there, and you can become a member, or you can become a member here on YouTube and support in that way as well. So with that being said, I'll see you guys in the next video.